Hey guys, welcome to this study lesson on paths and cycles, the last subtopic of graphs and networks of Unit 3. The dot points from the mathematics syllabus we're going to be covering today are 3.3.6 and 3.3.7. This lesson will consist of two parts. The first involves learning the new content, quite a few new concepts and definitions, but don't worry, nothing too tricky. And the second part will be applying this to problems you can expect in both the real world and your WACE exams. As we learned in the previous videos, networks in mathematics are an effective way of visually displaying the connections between certain objects or places. On a network like this, the vertices represent the objects or places of interest, and the connecting lines, called edges, represent how each point is connected or relates to the others. The first dot point, 3.3.6, requires us to understand some terminology before we move on. First up are walks. A walk is an ordered list of vertices, which must have an edge between each vertex. A walk is the simplest of walks, paths and trails because it can include repeated edges and vertices. The first vertex of the ordered list is called the origin, and the last is called the destination. Pretty straightforward, just think like on a map. Let's bring up our previous network. An example of a walk could start at A, then move to D, then to C, then back to D, and finish at vertex C. This would be written as W in brackets A, D, C, D, and C. So in this case, the origin is vertex A because it's where we began, and the destination is vertex C because that's where we ended up. Notice how this walk included both repeated edges and repeated vertices. This is completely fine. Next we have trails. A trail is similar to a walk in that it is an ordered list of vertices that must have an edge between each vertex. However, a trail cannot include repeated edges. Repeated vertices are fine, however. Here's an example. Starting at vertex C, then moving to A, then D, then back to C, and finishing at B, which would be written like this. Notice how the trail has passed through C twice, but doesn't have any repeated edges? Remember, trails have no repeated edges. Finally are paths. Again, paths are just a slightly more restricted version of a walk. So it's an ordered list of vertices. Each vertex must be connected by an edge. However, this time, neither repeated vertices nor repeated edges are allowed. An example of path could begin at vertex A, then go to B and finish at C, which would be written like so. To summarize these, just think about the walk as having no restrictions whatsoever. It is simply a list of ordered vertices. Repeated edges and vertices are allowed. Then a trail is a walk that has one restriction. It cannot have repeated edges. And finally, a path is a trail with one further restriction. No repeated edges or vertices. Now we've got walks, trails and paths down. There are a few variations on these that we need to know. Any walk or trail described as closed simply means the destination vertex is the same as the origin vertex, or in other words, it finishes the same place it begins, so it kind of looks like a weird loop. If you're fast, you may have noticed that this breaks the rules for a path. Paths cannot have repeated vertices, and if the origin and destination vertex are the same, then that vertex has been repeated. That's why there's a special name for closed paths, cycles. A cycle is the proper name for a closed path. The next characteristic is a connected graph, which is a network where every vertex within it is connected by an edge to every other vertex. In other words, it's possible to start at any vertex and get to any other vertex within the network. Note the connection between vertices can either be direct or indirect, meaning if you have to go through another vertex to reach the one you want, that's fine. Following this is the disconnected graph, which, as you guessed it, means not every vertex is connected to every other vertex. The bridge is an important one to remember, as a single network can contain many bridges, but they may be hard to spot. It is an edge within a connected network that, if removed, leaves the network disconnected. This is a connected graph, because all the vertices are connected to each other, so no matter which vertex I decide to begin at, it's possible to finish at any of the other vertices. But if the edge between G and F were removed, it would become disconnected, because it would be no longer possible to reach the vertex F. Therefore, the edge between G and F is called a bridge. There are a few types of network variations that you'll have to be able to understand and work with for the WACE. Edges can either be assigned a value or distance or not. This may come in useful when looking at road maps. Just because two different paths may have the same origin and destination doesn't mean they'll be of equal lengths. If the edges of a network have been assigned values, it is called a weighted network. Otherwise, it is unweighted. Another trait that can be assigned to edges is direction. In this case, some of the edges can only be travelled in the direction of the arrow labelled on the edge. Thus, it is called a directed network. Again, think of a road map where some roads are only one way and so cars cannot travel in the opposite direction. Now that we have the new content down pat, let's move on to the second part of the video, where we're going to apply this new knowledge to some problems, which checks off dot point 3.3.7. Investigate and solve practical problems to determine the shortest path between two vertices in a weighted graph by trial and error methods only. This dot point is pretty straightforward. Some of the most common network questions you'll be tested on involve finding the shortest path between two vertices. The ability to do this is actually the basis of programs such as Transperth Journey Planner. Think about it. You enter an origin and a destination, thus determining the possible paths available, and finding the program will give you the quickest trip by using a weighted directed network. This brings us to a quick side note. When we're looking at networks involving time, the critical path is defined as the path determining the minimum time required to complete the operation or reach the destination from origin. In other words, it's the shortest path when measured in time between the origin and destination. Here's a question you could expect to be in your WACE exams. The following network displays how 8 city train stations are connected and the distance in kilometres between each. It also includes an additional station under construction that isn't connected to the network yet. The first part asks us if the network is connected or disconnected. The second part, a track is planning to be built that would directly connect stations I and F. What type of edge would this new rail be in the network? And part B, give the shortest path between stations A and F and hence find the time taken to travel this path if the train is travelling at 50 kilometres an hour. Pause the video now if you want to have a go yourself. For part AI, we need to recall the requirements of a connected network, which are that each vertex in the network must be connected to every other vertex. A hint in the question was that station I isn't yet connected to the railway system, and when we look at the network, we see that the station represented by vertex I is isolated. So because vertex I isn't connected to every other vertex in the network, or any other vertex at all, this network is disconnected. Part AI says there is a new connection to be built between stations I and station F. This means that vertex I would become connected to vertex F, and as a result, every other vertex in the network, taking the network from disconnected to connected. Remember the name for an edge that, if removed, would leave a connected network disconnected is called a bridge. So, edge IF is a bridge. Part B is directly based off dot point 3.3.7, the one about using trial and error to find the shortest path. There are a few tricks you can use to cut down the number of trials you do. Firstly, don't get caught out on the fact that the network isn't to scale. Don't pick the path that is the shortest on your ruler. Okay, so the edge connecting F and H is 51 kilometers long, which is ridiculously long compared to the other edges. So the chances of it being in the shortest path are very low. This also applies to edges AF and AC when compared to AB. So we're going to assume the shortest path involves the edge AB. Let's begin the path by going from A to B. From B, there are 4 possible next moves, either to vertex C, D, E, or F. From here, it's tricky which to see as the best move without looking a couple steps ahead. So looking at vertex H, the shortest path is probably going to involve travelling along DH or GH, because they're so much shorter than the other options, CG and EH. From here, we can begin the trial and error process. Our first trial, assuming the move to B is definite, is A, then to B, E, D, G, and then H, which totals 32 kilometers. Our second trial is from A to B to D and finally at H, which is 33 kilometers. You may have noticed at this point that travelling from D straight to H is actually longer than going from D to G to H, even though the latter has more steps. Let's try one last path. Trial 3 is A to B to D to G and to h, which gives us 30 kilometres. This is the shortest of all our paths so far, so we're going to put this down as our answer. Remember, the question asks us for the path, which means we have to write out each vertex along the way. P is equal to bracket A, B, D, G, H. To get full marks for this question, we'll also have to give the time it'll take a train travelling at 50 kilometres an hour to cover the distance. To do this, we'll need to use the velocity equals distance over time equation and rearrange it to give us time. So 30 kilometres divided by 50 kilometres an hour equals 0.6 hours. Multiply by 60 to get it to minutes, which gives us 36. So it'll take the train 36 minutes. That brings us to the end of the lesson. I hope it was useful. In the next video, we're going to cover the final part of paths and cycles.